Okay, so as I mentioned before, this is a continuation of limits mixed with the average rate of change that we talked about. Really what we do is we kind of take the average rate of change and we shrink the interval. So let's just recall what the average rate of change did. So the average rate of change it was a formula, but we could also think of it from the picture. It was f of b minus f of a divided by b minus a. So that's the formula for it. And it's really kind of like a slope of a secant line between 2 points, right? So you might have some curve doing something, and if you have 2 points, an A, and then maybe a B somewhere up here. So again, your y values, if this is a function f of x, your y values are going to be f of a and f of b. What's really going on is you're finding the slope of the secant line connecting these two dotted points. So what you want to do with the derivative is you'd like to get it to where we can think about this as occurring at a single point rather than a pair of points. We want to find the tangent line to a point. So a tangent line would be a point that just touches it. And you're always going to be able to find these tangent lines for these smooth curves. And a lot of our continuous functions and examples of functions we look at are going to have that nice smoothness. So the idea of the derivative is to, as I said, think about the slope of a tangent line at a single point. And the way we do that is we use the concept of a limit that we learned about previously. What we do is we shift the interval, the distance between A and B, to essentially 0. And as we do that, we're finding the slope of the tangent line. So the notation for this is it involves that prime notation. So if you have some curve now and you're looking at just a single point A, what we've got is we've got the tangent line. And if we can find the slope of that tangent line, that is what the derivative is at that point. So the slope of the dotted line is, we would write f prime of A, and that would be the derivative of f of x at A. So what we do is, the way we get the limit is, instead of thinking about it as A and B, we think about it as A is our focal point, and then we think about, what if you were a little bit away from that, maybe a small value, something like h, then this point would be A plus h. So if h represents the distance between A and a nearby point, taking the limit as h goes to 0 gives the derivative. This is actually how we find the derivative function. And what would you be doing? Basically, we'd be doing the limit as h approaches 0 of f of a plus h minus f of a over a plus h minus a. So the a's cancel in the denominator, and you're just left with the limit as h approaches 0 of f of a plus h minus f of a over h. So this is actually the formal definition of the derivative at a point. And if you want to do it for a function, we don't think about a as just being a single value. We think about it as being a variable. So that's going to lead us into the definition of our derivative. Sometimes that quantity, so the limit and the whole thing together is the definition of the derivative. If you just looked at the rational expression, f of a plus h minus f of a over h on its own, sometimes that's known as the difference quotient. So you'll see that terminology from time to time. But yeah, here's the definition. And when we compute some derivatives by definition, it'll be similar to those limit examples we looked at last time. But once we've done a few, we'll understand the shortcuts for the different classes of functions, and we'll have a bunch of different rules so that we can do them more quickly. So the derivative function f of x is defined by f prime of x, and it's exactly that limit. The limit as h approaches 0 of f of x plus h minus f of x over h. So again, you can see if you look at this limit, it's in indeterminate form already, right? You can't just plug 0 in for h because there's an h in the denominator. So whenever you're trying to compute a derivative, the goal is to cancel out that h in the denominator somehow. And we're going to do it using the same sort of tricks we had when we were looking at limits before. You know, we're going to be looking at factoring, expanding, multiplying by the conjugate, and getting a common denominator. So example, let's compute the derivative using the definition. So whenever they say using the definition, that basically means the long way. So if you know some of the shortcuts already, you might know the answer, but we still have to go through the steps. So the first one, let's say we have f of x is x squared. So, well, f prime of x, according to this definition, is going to be the limit as h approaches 0. And then you need to plug in x plus h for x first. So that would be x plus h quantity squared minus x squared over h. So there's a little bit of function composition there. And then what happens is we need to expand. Remember, x plus h, it's not x squared plus h squared. You actually need to write it out in FOIL. So this is going to be the limit as h approaches 0. When you FOIL that out, you get x squared plus 2xh plus h squared minus x squared over h. And both of those x squareds are going to cancel out. And so we can factor from the remaining terms. We can take an h out of the top, and you'll have a 2x plus an h. And then you can finally cancel your h's. So before these canceled. And that'll leave you with the limit as h approaches 0 of 2x plus h. Now that the h in the bottom is canceled, you can plug in 0 for the leftover h, and we see that the derivative there is just 2x. So the derivative of x squared is 2x. Let's try one more polynomial. It'll get more complicated, but it'll look more complicated, but really it's not any harder. It's just more things because there's more terms. So if we look at, say, g of x is 7x squared minus just regular x. Well, then, give myself a little bit more room this time. G prime of x will be the limit as h approaches 0 of 7 times x plus h quantity squared minus x plus h. So that's the x plus h part. Then you need to subtract the whole regular g of x formula. So there's a lot of parentheses going on here. So minus 7x squared minus x, and then everything is being divided by h. So again, we have to FOIL the x plus h squared, and the other two sets of parentheses, you need to distribute the negative sign to remove the parentheses. So this is going to be the limit as h approaches 0 of 7 times quantity x squared plus 2xh plus h squared minus x minus h minus 7x squared plus x. So at this step here, the x's have canceled, so those drop out. Continuing, we want to distribute that 7. So we have the limit as h approaches 0 of 7x squared plus 14xh plus 7h squared minus h over h. Oh, I forgot the minus 7x squared. I knew I missed something. So minus h minus 7x squared. So your 7x squared at the beginning cancels with the minus 7x squared. So these cross off. So then you can factor out the h as we did in the previous example. So we'll have h and we'll have 14x plus 7h minus 1 divided by h. So now the h in the denominator, the pesky h that causes the problems, that one is canceled out. And you can plug in 0 for the remaining h, right? So you have 14x plus 7 times 0 minus 1, which is just 14x minus 1, which is your derivative. Any questions so far? Okay. Like I said, these limits are kind of long, and we'll go through them once, and then we'll learn some shortcut rules, and then immediately you would know how to take the derivative of that, and you wouldn't have to go through all this rigmarole. But it's good to practice with your limits the first time you see them. Okay, so let's go through one with a square root. So let's say we have h of x is the, let's say this is, let's say it's 8 times the square root of x. So anytime you have a square root and you're involving a limit, you want to keep in the back of your mind that certainly multiplying by the conjugate is going to be a possibility. And that's definitely going to happen here. So this is going to be like the rationalize the numerator limit we did previously. So h prime of x is going to be the limit as h approaches 0 of 8 square root x plus h minus 8 square root x divided by h. So now to compute this limit, this is where we need to rationalize that numerator. So hopefully something will be left over to cancel with that h in the denominator. So we'll multiply by the conjugate. So 8 square root x plus h plus 8 square root x over 8 square root x plus h plus 8 square root x. So remember on the top, so let's just put a side in there. If you have an a plus b times a minus b, this simplifies to a squared minus b squared. So the top will actually just be the limit as h approaches 0 of 8 square root x plus h squared minus 8 square root x squared. And the bottom, I'm just going to write those next to each other, the 8 and then the 8 square root x plus h plus 8 square root x. So on the top, when you square 8, you get 64. So we're going to get 64 times x plus h. The square also cancels the square root. And then minus 64x here. And then the bottom remains the same. So on top, you're going to get 64x plus 64h minus 64x. So the 64x's will cancel. So I'm just going to have 64h on top over h times this 8 square root x plus h plus h square root x. So after all that work, we see that the h's cancel, or at least the h that we care about. So the remaining one we can plug in 0 for. So you have 64 over 8 square root x plus 8 square root x, because the first h turns to 0, so it's just 8 square root x. So you have 64 over 16x, 16 square root x, which is just 4 divided by the square root of x. So that's it for C there. All right, let's do one with a fraction. The fraction ones get the common denominator, and then pretty much that'll be it for our practice using the limits, and then we'll start to look at the shortcut rules, namely the ones involving polynomials. So let's say f of x is 3 over x. So the derivative here, f prime of x, will be the limit as h approaches 0 of 3 over x plus h minus 3 over x divided by h. So the first thing we want to do is get a common denominator. So a common denominator in the numerator of the top part of the fraction, the complex fraction. So we want to combine the 3 over x plus h with the minus 3 over x. So the way we're going to do that is we're going to multiply the first fraction by x over x and the second fraction by x plus h over x plus h. So we have the limit as h goes to 0 of 3 over x plus h times x over x minus 3 over x times x plus h over x plus h. And this is all being divided by h. So we can now combine those because they do have a common denominator. So the top fraction is going to be 3x minus 3 times x plus h. And now we have that shared denominator of x times x plus h. And all of that is being divided by h still. And then, if we want to put these together as a single fraction, we can, because you can think of h as h over 1, right? And then we could think of this fraction being divided by this fraction, right? And then recall, if you do a over b divided by c over d, this is the same thing as a over b times d over c, right? You just flip over the second fraction, it becomes multiplication. So what I'm going to do is I'm going to say, all right, well, I can just flip over the h over 1 and multiply by 1 over h. What happens in the top? Well, basically I'm going to have 3x minus 3x minus 3h over x times x plus h. And then again, remember, I'm going to be multiplying by 1 over h now. And that works out for us because the 3x's cancel. So we have minus 3h over this 3x, over just x times x plus h. So these h's are gone, and then you can plug in 0 for the remaining h. So you'll get negative 3 divided by x times x, which is negative 3 over x squared. And that is the derivative of 3 over x. So any questions on those long computations using the limit? You may have to read through them once or twice more. There's a lot of steps, just a lot of algebra going on, really. I've often said that the hardest part of calculus is algebra. It's where a lot of the details are. So let's talk about shortcut rules for multiplying by polynomials. So the first one, and right now we're just talking about polynomials. We're going to have different rules when we get to different classes of functions. So exponential rules are going to have their own derivatives. logarithmic functions are going to have their own derivatives. But polynomials behave really nicely. So the first one here is this power rule. So it says if you take the derivative of something that looks like x to the n, what you will get is n times x to the n minus 1. So we saw that previously in a couple of different scenarios. Right? If we were going to take the derivative of x squared, the very first one we did, what did we do? We brought the 2 down, and then we subtracted 1 from the power. That's why we got the derivative as just being 2x. But this will work for other powers as well. Let's say we had x to the 6th. Then the derivative would be bring the 6 down in front, and then lower the exponent by 1. It would be 6x to the 5th. It actually worked. It'll work with one that's similar to one we'd already done. We did 1 over x. Let's think about 1 over x squared. Could it work with something like this too? Well, if you rewrite the 1 over x squared as x to the negative 2nd, now it looks like it's in the form x to the n, and you can apply the power rule. So you would get negative 2x to the negative 2 minus 1. So the derivative here is actually negative 2x to the negative 3. So that is the power rule, and those are some examples. We also have the constant out rule, which basically says constants we can kind of ignore and just apply the regular rules and multiply the constants back at the end. So the constant out rule says if you have a constant times a function and you want to take the derivative, you can take the constant out and just do the derivative of the function. So, for instance, if I were trying to find the derivative of, say, 7 times x cubed, I could just say, okay, well, forget about the 7 for now. How do I do the derivative of x cubed? Well, I just learned in rule number 1 that should be 3x squared. So then I just do 7 times 3x squared, and I get my derivative is 21x squared. So I was allowed to just temporarily forget about that 7 and focus on the part that contained the x to take its derivative. And rule number 3 is a sum or difference rule. So basically, this allows us to go term by term. So if you want to take the derivative of f of x plus g of x, you can just do f prime of x plus g prime of x. So you can do each of them separately and take their derivatives term by term. Now, the same thing won't work with multiplications. When you have 2 terms multiplied together, you can't do f prime of x times g prime of x. We'll come back to that later. That is known as the product rule. There's going to be something additional we're going to have to do there. So although it behaves well with constant multiplication and sums, it's not going to behave as well with multiplication or division. What's an example of this working? How about if we want to take the derivative of, say, 10x cubed plus 8x squared? Well, this says we can just do the derivative of each one, right? So we can do 10x cubed, its derivative, plus the derivative of 8x squared. And so we know basically this should be 10 times 3x squared plus 8 times 2x. Applying the power rule, and then we have 30x squared plus 16x. Okay, so there are a couple of other special cases of number 1. So things that are polynomials that don't exactly kind of work according to rule number 1, but I would call them special cases. So 2 special cases. Of rule number 1. So if you want to take the derivative of any constant, you're taking the derivative of just a constant on its own, that derivative is equal to 0. And one way to think about it is the derivative is really the slope of a tangent line, And if you look at the graph of any constant, it's exactly a horizontal line. So y equals c is a horizontal line. Horizontal lines have slope 0. So for any linear function, the derivative is going to be exactly the slope. And that brings us to the second case 2. If you have, say, the derivative of, say, some mx, it's going to be derivative m. And if you think about that, if you had y equals mx, it would be some line through the origin, and it would have slope exactly m. So if you have the derivative of something with an x next to it, it's just the coefficient. And if you have the derivative of some constant on its own, not multiplied with a function of x, then the derivative is just 0. So let's go ahead and look at some examples where we differentiate. Differentiate, again, just means find the derivative. Just a fancy word for that. So A, let's say we have, I don't know, 17x to the 4th. Again, we would just leave the 17 on its own and then take the derivative of x to the 4th, which is 4x to the 3rd, and then you could multiply your regular numbers there. So what did we get? 68 something, or yeah, 40 and 28, 68 x cubed. Now, what about something like, let's say, 9x cubed plus 15x minus the square root of 7. Again, you would go term by term here. So we would say, okay, well, we can do 9x cubed. We can do 15x. And we can also do the square root of 7. So 9x cubed, pretty standard. Just 9 times 3x squared, which is going to be 27x squared. And then 15x, this is one of those special cases. It would be that part would be like a line with slope 15. So you just get the coefficient. So the x drops off and we're just left with plus 15. And then the square root of 7, the derivative of that is 0, right? So I'll write a plus 0 just to emphasize that this time. But a lot of times you'll just drop to the final step. And that's just because that's a constant. Okay, what about if we did the derivative of, say, the 4th root of x? Now, anytime you have a fraction or a radical, what you want to try and do is rewrite the function using your exponent notation first before trying to take the derivative. So this would be, we're really trying to find the derivative of x to the 1/4 power. Right? And so to take the derivative, we bring that 1/4 down in front, and then we do 1/4 minus 1. So our derivative here is 1/4 x to the negative 3/4. And, you know, that's, if you want to rewrite that in radical notation, you could try and practice that. That would be 1/4 times the 4th root of x cubed. So I won't typically require that, but sometimes you'll see it as in say like answer keys. A lot of times they'll rewrite things using radical notation. Okay, D. Let's say we have something like I don't know, 5x squared minus 2 divided by x. Now, again, this is a quotient, so we don't really have a way to find derivatives of any quotients yet. Like I said, that's going to be a rule for later on. But what we can do is we can try and use algebra to simplify things. And if we can rewrite them as multiple terms with x to a power, then we should be able to take the derivative. So that's what we do. We just kind of break this apart into 2 terms using the common denominator, 5x squared over x minus 2 over x. And then we can rewrite that again. 5x squared over x is just going to be 5x. And 2 over x, we can write that as 2x to the negative first power. Because we want to try and write everything as x to a power to apply that power rule. If you cannot write it as x to a power, then you cannot appeal to that rule. And then the derivatives term by term, 5x just has derivative 5. And the second one, bring down the negative 1, so that becomes a plus 2x. And then subtract 1 from the power. It's going to be negative second as the new exponent. So again, we could write this as 5 plus 2 over x squared if we wanted. And that is pretty much it for derivative practice today. We went through a lot of examples, but like I said, there's a few on the homework. This is the end of what's on the third homework. So try that. Use the rest of the time you have today to attempt some problems there. And then we will come back to that on Friday, and I'll answer any questions you might have or ones that have stumped you that you have not been able to figure out.